Okay, here we are in section 12.1 for our last video. Here we're going to actually put this together and do a problem. So on number 10 we have ideal proportions. The students in Mr. Shank's class measure the arm spans and heights in inches of a random sample of 18 students from their large high school. Some computer output from a least squares regression analysis on these data is shown below. Construct and interpret a 90% confidence interval for the slope of the population regression line. Assume that the conditions for performing inference are met. So we're going to go through that same four-step process that we began way back in chapter, I think it was 8. In the beginning of that, we want to do our state. When we're stating, we want to talk about our parameter of interest, kind of set the stage for what's going on. It's going to later on help us out as well. So we're looking here at beta, which is the slope of the population regression line relating heights to arm spans for students in this high school. Then in our plan stage was one of the places we usually are checking conditions, but since we already know that our conditions have been met, we don't have to worry about that. So we just want to keep in mind what our test is that we're going to perform. And for this one, we're going to be doing a linear reg, or a lin-reg t interval. So a linear regression t interval for beta. Keep in mind what that parameter of interest is. And then in the do, we should be performing our math. In order to do that, in the t interval, we always need our degrees of freedom. Remember, degrees of freedom is n minus 2. The way I remember that is we're normally doing n minus 1, but we also normally have just one variable. Now that we've moved into two variables, we're going to have n minus 2. That's the way I remember it. Might be helpful for you. N minus 2 for two variables. So bivariate data, regression, we're using n minus 2. In this case, we have 18 minus 2, which gives us 16 for our degrees of freedom. Then I'm going to set up my formula. I'm going to move this a little bit. I'm going to set up my formula. Remember, here in the resource packet, on the second page, I always have this given to me. I just need to know how to piece that together for what I have now. So statistic in this case is going to be our b, the slope that we have for our regression line, plus or minus our critical value. It's still our t critical value, so we're going to go to the table to find that. And the standard deviation of the statistic is going to be the standard deviation of b. Both of these are going to come from the computer output, and our critical value is going to come from our t table. So we have b plus or minus t critical value times the standard error of b. Now b we get from our computer output is 0.84042 plus or minus our t critical value. Again, I'm going to my t table, and in my t table I'm going to look at my degrees of freedom. For the 90% confidence interval, I move up to 16 for my degrees of freedom, and I have 1.746. Then the standard error of b, remember we stay along this line, and standard deviation is 0.08091. Now if I put that into my calculator, to fit in 0.84042 plus 1.746 times 0.08091 gives me 0.9817. Now I'm going to arrow up here, press enter, and it's going to re-input the same thing, and then I'm going to arrow over to change that plus to a minus. and enter again, and I get 0.6992, and that's my confidence interval, 0.6992 to 0.9817. And then as always, I'm going to give this solution in context. So we are 90% confident that the interval .6992 to 0.9817 captures, sorry, that kind of got off, captures the slope of the, and I'm going to keep writing all of that stuff I had written up there in beta, of the population regression line relating heights to arm spans for students in this high school. So a lot of the mechanics that we're doing here is just like we did before in the previous chapters with confidence intervals. It's just where our numbers are coming from that has changed. The other big thing is my suggestion to remind you, n-2 because we have two variables. n-2 for two variables. That's it for section 12.1.